In this video, we're going to talk about intermolecular forces of attraction. You should already be able to draw Lewis structures and do anything that has anything to do with bonding for all compounds. But by the end of the video, you should also be able to identify the type of intermolecular force used to hold multiple molecules together and determine properties based on those intermolecular forces. So, intermolecular forces of attraction are weaker than bonds, but are responsible for holding a substance together. The strength of an intermolecular force, or IMF, determines properties like melting point, boiling point, hardness, solubility, and phase. So let's fill in the blanks. Substances with strong intermolecular forces have high melting points, high boiling points, and are most likely the solid phase at room temperature. Liquids will have a strong surface tension and a high viscosity. Viscosity means how thick it is. I almost forgot. There is a question in the video. So how does that relate to this video? Pretty neat, right? So we think that these intermolecular forces and bonds might be at play. Let's talk about what the forces are. The first type of force is London dispersal force. It's the weakest of the attractions in mostly covalent or nonpolar molecules. The electrons of one atom will attract the nucleus of another, and this causes a temporary shift of electrons, making one side of the molecule positive for a slight moment and the other side negative for a slight moment. If you know that that happens, then opposites attract and it will attract each other. The more electrons are, the stronger the force will happen. So the more electrons you can polarize, the more polar it will be for that split second, and it will attract each other. For example, CH4 only has 6 electrons for carbon and 1 electron for each hydrogen, and so therefore it doesn't polarize as well, and therefore it is a gas. Whereas C8H18 has way more electrons, it will polarize a little bit better and be a liquid. C50H102 is a solid at room temperature because it polarizes so many more electrons, creating even stronger temporary polar molecule. Temporary electrostatic attractions between the temporary plus and the temporary minus. And here's another picture in its cloud version. A helium atom might actually attract another helium atom if the nuclei get attracted to the other atom's electrons. They'll shift a little bit for a minute, and you'll get a slightly negative side where the electrons are, that's the dots, and a slightly positive side where the nucleus is, attracted to a slightly negative side of the second atom, and a slightly positive side of where its nucleus is. Again, does helium do this very well? No, because the helium only has 2 electrons. So it doesn't do this very well, and we have evidence of that. Helium always likes to disperse, and that's why your balloons only last so long, right? Our second type of force is dipole-dipole attractions, and these occur between polar molecules. Note that polar molecules also have those London dispersal forces, but the dipole-dipole case is probably more stronger in most cases, not all. The greater the polarity of the molecules, the greater their forces are. So together with London dispersal, these are called van der Waals forces. Originally, we didn't know the difference between them, and van der Waal figured out that there were forces that keep molecules together, but we didn't know the difference between the polar and the nonpolar yet to distinguish. So remember that the rule is just opposites attract, whether there is a permanent polar particle, whether it be the dipole forces, or if it's a temporary one, which would be the London dispersal force. These are weaker forces than the actual bond themselves. There's a special case of dipole forces called hydrogen bonds, and this is what we focused in on last year in our year 1 class. A special intermolecular force exists between hydrogen, one of our less electronegative elements, nonmetals, and then FO and N, some of our higher electronegativity elements. And so we always remember hydrogen bonds were fun because they had really high melting and boiling points, which means they have really strong surface tensions for lizards to run on, or they have they're relatively viscous, right? Thick enough for us to drink and coat our throats when it hurts. We also have another special case of intermolecular forces occurring between carbon atoms and silicon dioxide molecules. These form network solids with stronger than the van der Waals forces that you would have originally thought they had. They're actually covalently bonded. So one of my favorite network solids is the buckyball, which you've probably seen in my classroom, where carbons are bonded at a 120-degree angle from each other. Kind of like the graphite in one of the carbon's other allotropes. So they're bonded at like sp2 hybrid angles in sheets, and the sheets are kind of rounded out to make this buckyball shape. Or it might be a sp3 arrangement where the bonds happen 4 times, right? And in that case has 109.5 degree angles, which are not as flat as a planar was, and then that's how you get diamonds. So common network solids that we see where they're really strong and resist melting and boiling and have really viscous structures would be diamond at the sp3 hybrid, Silicon dioxide, also similar, sp3 hybrid, so it behaves a lot like diamond. And notice silicon is in the same group as carbon, that's why it behaves that way. Silicon carbide, same thing. If silicon is mixed with carbon, it will have a similar structure. And then the carbon that does an sp2 arrangement, like in graphite or in buckyballs. Our next type of attraction occurs between ionic compounds that are really strong ionic bonds and polar compounds that have weaker covalent bonds. And what happens is the polar substances like water can ionize the ionic substances due to these plus-minus attractions, and that's why polar substances and ionic substances are mostly miscible or mixable. So what you're seeing here is the water is ripping apart the sodium from the chlorine. The positive hydrogens are attracted to the negative chlorine, and the negative oxygens are attracted to the positive sodium. So a summary of strength from strong to weak, we have the ionic and metallic bonds, then covalent bonds. There's wiggle room here. If there's enough bonds, the covalent bonds might be stronger than the ionic and metallic. But if we're going one for one ionic bond is probably stronger than one covalent bond. Those are both stronger than the network solids for sure. And the network solids, one network solid, one bond net, would be stronger than one ion-dipole force. One ion-dipole force would be stronger than one hydrogen bond. One hydrogen bond would be stronger than one dipole-dipole force. And one dipole force would be stronger than one London dispersal force. And that's all because of what kind of charges we have. We have no charge change, and so we make a slight charge. We have an actual slight charge all the time. We have an actual strong but slight charge all the time. We have actual charges and slight charges, a special case, no charges, and then charges, complete charges. So we're going generally from no charge to charge, no charge to charge again. At this point, you should be able to identify the type of intermolecular force to tell me some properties of compounds.